we are going to see is the introduction to the deep learning. So I myself is N.Sivasankari, working as an assistant professor in the Department of Electrical and Electronics Engineering, BSc. This is the outline of this presentation. It is a presentation which deals with the supervised learning, unsupervised learning and reinforcement learning. And supervised learning will be seen as convolutional neural network and sequential learning. RNN is recurrent neural network and its extensions, and unsupervised will be having this autoencoder as well as the stack DOC autoencoder, mostly the supervised learning. So here it makes use of this labeled inputs and outputs, whereas unsupervised learning. So this unlabeled data is being, the labeled data is not used, unlabeled data is used, and it finds some hidden features that is being present in the data. And reinforcement learning usually learns based on this trial and error. So the traditional recognition models, they make use of this handcrafted features and this simplified distributed classifier. And this approach has the main limitation, it's very tedious and it's also costly to develop these features. And they are usually highly dependent on one application and it cannot be transferred easily to some other applications. And it's very simple. So this coming to this deep learning is one of the subset of this machine learning, and it seeks to learn the hierarchy representations that's being present in the data, and it extracts it automatically to the multiple stages of this feature learning. The hidden features are automatically extracted and it passes on to these multiple stages of features. And mostly it has this consists of low-level features, mid-level, high-level, and it makes use of this triangle classifier panel getting this output, and this the feature visualization of this convolutional network that's trying using the image that is shown in figure. So this is a hierarchical representations. So from the low-level features to mid-level, high-level triangle classifier, and then to the output. This is the increasing level of abstraction what we have. The hierarchical representations with this increasing level of abstraction, each stage will be making use of a kind of triangle non-linear feature transform. The image recognition, that's from pixel to edge to text on object, and object, and the text means character to word, to class, it is, and to story. So the deep learning, so it usually offers so many layers, there's the hidden layers that's being present, and it's very deeper than the traditional learning method. So this is the example of this non-visual context that's makes use of this hierarchical representation. So it's brutally inspired by nature. So we need to understand what are all the details that's very important, and these details are merely so not the results of this evolution. So each model that's being presented in this deep learning transforms the input representation into a next to higher level. So it's very similar to that of a human context. And this convolutional neural network, so under that we will be seeing the supervised CNN sequence modeling. Why do we need this recurrent neural networks, and what are the sort of extensions, and how we can do that. So the convolutional neural network, so this is the input usually will be having very high dimension, and it consists of so many dense fully connected layers that needs a large amount of this input parameters, and it is there are special type of neural networks, and these hidden units are connected to a local that is the receptor field. So the number of parameters which is needed by CNN is much smaller. So this fully connected layers will be having this for 200 cross 200 images. So we'll be having 40,000 hidden units, and this pi cross pi kernel will be using this memory kernels, and this feature maps is almost 2,500 parameters basis of it. The three stages is that the input layer, this convolution as well as the next layer. So this convolution layer will be having this convolution stage, the detector stage as well as the polling stage, and here in the convolution stage we will be using this affine transform, and this ReLU, that is the rectified linear, that's the ReLU we will be using for this detection stage and the polling stage, and next to this next complex level. And this non-linearity, usually this transform which we use in the rectified linear array, the tanh functions, and the pooling. So it's output of the summary statistics of this local input. So here it may be either it may be an average pooling or a maximum pooling. So this convolution operation which we will be doing it in the CNN for activity array. So here the kernel 2D kernel You see this WX, Y, Z. So this is the input matrix, So it's performing this convolution. So you see that it's simply a matrix multiplication. For example, this is AW plus BX plus this matrix multiplication. It's EY plus FZ and this side. So BW, then BW plus CX plus FY plus DZ, and similarly this CW plus this DX plus DY plus HZ. So in this way the multiplication goes on. So you see this is the convolution operation. So you see this kernel, 2 cross 2 kernel here. So usually this multiple convolutions is one of, there are multiple feature labs and one for each convolution operator. And usually there are multiple feature maps, so each one having at least one convolution operator. So this is the activation functions which will be using this tan h as well as value. So it's from 0 to some maximum value, this tan h function. So the maximum pooling, as you see this, you see from this local receptive fields. So the important features are extracted through and we'll weight sharing then to the pooling layer and the convolution to pooling. So the maximum pooling, so here it's the maximum output within this rectangular neighborhood. So the average pooling is the average output of the rectangular neighborhood. So this is almost what's the distance from the central pixel. So space pooling region, so if it's greater than 1, so it's the pixels are apart and the X layer is roughly k times. It's fewer inputs to process that may. If it's fewer input, that may lead to down sampling. So this is this image net. So here we'll be having multiple feature maps for the convolution layer and each will be extracting the free features at different levels. So the higher level layers usually the mapping of the features is done with the lower level layers. So the deep CNN is AlphaGo policy network. So here we'll be having a policy network and value network. So the layer 1 will be using a 5 cross 5 kernel with 192 filters and layer 2 with 3 cross 3 kernel with 192 filters and till up to 13 with 1 cross 1 kernel. The value network is also having a similar architecture to that of your policy network. What's the need for this recurrent neural networks and what are it and what are the extensions and how can we do that? So it's mainly, so we are assuming that your training and test samples are different. So at each data point which will be processing various state of network. So mainly it rely on the examples that are based on the vectors which are having the fixed length. We need to model the data either with the temporal, the time-based details or some other sequential features, and which will be having this various inputs and output. So the length, that is the feature. That's the input and output vector, that's the length vector field, the length should vary. So the examples, whether it may be a video frame or the audio snippet or else from the words from sentences. And this coming to this ordinance, so we will be having this input layer, middle layer and output layer. And so here a feedback from this previous layer to the next one. So they have the ability of processing the sequential data. This is mainly for the time series data. We'll be going for the ordinance. They allow the memory by the previous inputs to process the network internal state, and that influences the output. That's from the previous input that will be fed back. So that influences the current output. So here we'll be having this multi-layer perceptron model. So and coming to this, they can also be converted into a normal feed forward. And this is an unfolded this recurrent network. So here the connections from the input to hidden is W1 and those from hidden to the other hidden layer W2 and from hidden to the other output layer will be marking as W3, and the weights are used during each step and these bias weights are omitted for clarity. And coming to this back BPTT is often used to learn RNN, so it's one of the extension of this back propagation. So here Y of t represents the output and this H of t is the hidden layer. So S of t is the single. Then here you will be using the standard functions and the error is calculated, that is the logarithmic of this output. So the total loss will be the sum of errors which will be accounting in each time step. And regarding this gradients, so at each step we will be calculating it and we are making use of the chain rule. And so here this is what here. So the weight is used every step up to find out the output and you need to back propagate the gradients. For example, if you are moving from t is equal to 0 until it reaches t is equal to 3. So that is being calculated at each step. So the layers and type steps of these deep neural networks, they relate to each other. That is the continuous multiplication, derivatives of functions, that is the partial derivatives of the error functions. Regarding to your weight factors that are susceptible to the vanishing. So the state that those that does not contribute, so you'll end up not this learning this long range type of dependencies. And coming to the how to solve this is you can reduce by the proper initialization of the matrix, you can really do that. And this ReLU, instead of using some other sigmoidal or tan H, we can use of this rectified linear, that's the relative function. So since it's either 0 or 1, so it's not likely to suffer from this vanishing radius. And next week we'll be seeing, before that, there is the bidirectional recurrent neural network. So this is another one more time. So here we'll be having these two types of layers. That is the training sequence, both forward as well as the backward, and we having two separate recurrent neural layers. That is the past as well as the future context that will represent, that will determine the output. Then the vanishing gradient problem. So this also prevents the standard from learning. So here we are to compact with that. We will be going for this LSTM, that is the long short memory network. Here we will be having this input layer and hidden as well as the output layer. So you will be having this input gate, memory gate, forget, file memory, and the output gate. So 5 type of things. So the new memory, as we all know, it's we will be applying this the tan H, that is the the input word which you are using, so it makes use of this past hidden state, and it will generate a new based on the past state, that is here. That is your present. WC of x of t is your present state, and this UCH of that is from the hidden layer, that is the past state is taken from the hidden layer. So now this will become the new input. So the forget what it is that it will look up your input weight as well as your hidden past hidden state and makes whether you need this past memory. Yes, if you are getting the residue of h of t minus 1, whether you have to forget the past one or else you have to keep it. So that's the function of your forget gate. And final memory, so it will take the advice in the forget gate, and accordingly it will forget the past memory, and it will take the advice of the input gate, and accordingly it will pass on to a new memory. So it's both the results, so it will be taken into account in order to produce the final memory. So output gate, so it makes the assessment what's the part of the memory that is need to be kept and what's that's being present in the hidden state. So usually x of the w naught x of t is the current state, and u naught of h of t minus 1 is the previous hidden state. So the hidden state here will be applied in tan H function. So coming to this conclusive part of this LSTM, so it contains all the normal flow of decorum network in a gated cell, so can be storing or read from a cell much more like that in a computer's memory. So the cells can learn that allow the data to either to enter or leave or to be deleted through the iterative process back propagating and adjusting the weights via gradient descent. So the vanishing gradient problem also it is able to compact with that by allowing the recurrent to continue to learn over many steps, so thereby causing a channel to link the cause and effect. So these are all of the applications of this ordinance, let's say the machine translation and machine question answer. So the translation, so the input will be giving a sequence of words that is being presented in language, and the output is a sequence of words. What is to be presented in the target. So here making use of this encoder as well as the decoder architecture for this, and in the encoder side, the RNN will encode the input sequence into the hidden state, or all the hidden features that's being present, and in the decoder side, the RNN, the hidden state of the sentence, that's the language that's being present, the input and the output of the translated sentences. So it matches that. Visual question answering, so it's based on the visual system, the AI will answer the question. So here you look at this funny diagram. What's the statues made of? We all know it's not made of ham, it's made of bananas. So it's the way. So you're begging given an image, so the NLP will question, and the task is to provide an accurate NLP answer. So output either it may be conditioned, here you see this the left hand side is a text, and the textual inputs that we can use. So it's used to encode an image, and RNN is used to implement the encoding of a sentence. So the unsupervised learning, autoencoders, deep auto, denoising, stack denoising. So autoencoder is usually feed forward neural network. So the input hidden part corresponds to an encoder and hidden output part acts as a decoder here. So it's mainly constitute so many encoders and decoders with multiple hidden layers, and here the grading is also very small as it passes through so many layers. So the learned feature activations of this restricted Boltzmann machine. So here after the training, the RBMs are unrolled to create a deep autoencoder. So that is also fine-tuned using back propagation of error, that is the error from the output moving towards the input. So by adding this noise, it can force this autoencoder to learn the more robust features, the high level of representations also you can do it. So the performance of this denoising, so it requires the feature extraction, that is the one that captures the useful feature that is being present in the input. So here it's mainly advocated to investigate the training criteria for learning to extract the useful features that constitutes the better higher level of representation of the output. The last function is being given. So like deep autoencoder also, here also we can stack the multiple denoising of autoencoders in order to form a stacked denoising autoencoder. So this is the no noise, that is 0%, and the noise ratio is 13% for this different noise ratios. The applications is we will be having this Atari and AlphaGo. So coming to this reinforcement learning, here reinforcement consists of 4 entities. There is the environment, the observation or reward, actions and agent. So an agent usually interacts with an environment, so and it learns from the environment and it either maximize the reward. So previously, so based upon this actions, previous actions are based on the states, so it will be receives the reward signal. So here you are making use of this policy functions, so that that are the selection of the what action is to be selected for a given state. So that each value function, so they produce the reward. So what's the total reward for a particular state, what is the reward and what is the action that is to be done under this policy, whether the action is good or not. So here the approach is either it may be a policy based, value based or model based. So this is the way how we will be using this oral, that is the deep learning. So just from the raw observation where which it learns from the environment and suitably the action is taken. So based on the stage, so it will be getting a reward. So the value function of this Q network, that is state action, and we are defining the objective function here. This is softmax and Q learning gradient you will be using. And the input state, we all know it is a raw pixel, and this output is for Atari. So the input is the last raw pixel from the last frame, and the output is a joystick position, and the reward is what is the score for each movement, what is the score. So this one is for this Monte Carlo tree search. So it reduces the searching space by it predicts what will be the opponent's move. So this AlphaGo, so it's self-learning as well as this RL. So what's the difference? Prior probability. So we will be building a global frame of this leaf node situation. So this what's the role of policy and what is the self-learning and oral and what is this value network. So 13-layer CNN we will be using that. That is what are the features extracting here is tone color, what are the turns, liberties, the size, liberty after that is ladder capture, escape, sensibleness, player, color, and this self policy as well as this oral, that is the reinforced one. So combined with that, this what is this oral versus this SL is being compared. So as we all know that the sampling to generate the grade. So regression problem will be prediction of this the prices will be doing that, and it trains 5 million batches of 32 positions. So what is that? Gains 5% is that. So these are some of the few examples. These are all the references.